It's a great pleasure to be here at this very nice conference. I was also quite surprised to see all these beautiful buildings on campus. Okay, so I'm going to be talking, given the diverse nature of the audience, I decided to give a rather pedagogic talk where I try to convey the basics of the quantum Monte Carlo method. So I will have no applications in my talk. When I planned the talk, I was actually originally thinking that Ken would be talking about quantum Monte Carlo applications, but I see from the program that in fact he's going to be talking about something completely different. Okay, so here's an outline of my talk. I will start by sort of telling you where the place that quantum Monte Carlo methods occupy in the scheme of electronic structure methods. I will give you an introduction first to just Monte Carlo methods before I talk about the quantum Monte Carlo methods, and I will mostly focus on two different quantum Monte Carlo methods, variational Monte Carlo and projector Monte Carlo methods. And again, within projector Monte Carlo methods, two different methods, in one of which the walk is done in real space, and in the other, the walk is done in orbital or determinant space. Then I will talk about the sign problem that Martin alluded to in the first talk. And then I will talk about a quantum Monte Carlo method that tries to overcome the sign problem. And I will end by talking about, if there is time, a comparison of different projector Monte Carlo methods. Okay, so electronic structure methods. There are three broad classes of electronic structure methods: quantum chemistry methods, density functional theory, and quantum Monte Carlo. Now, I don't really know how many people work in each of these areas, but I've tried to give you a very, very crude estimate. And the main point is that the number of people who work in quantum chemistry methods and density functional theory is far larger than the number of people who work in quantum Monte Carlo methods. So these methods are much more developed than quantum Monte Carlo methods, but that also means that quantum Monte Carlo methods are an interesting area to do research because there's more scope for improving the methods. In particular, the difference is bigger between the number of users in the different methods than in the number of developers, which reflects the fact that these methods are more developed, and there are nice black box packages that people can use for these methods, and not so much so for the quantum Monte Carlo methods. Okay, so what are some of the characteristics of the quantum Monte Carlo, of the various electronic structure methods? The simplest quantum chemistry method is Hartree-Fock. That's not accurate enough for most purposes. But there are various improvements that one can make. In particular, there are systematic improvements that one can make. So configuration, interaction, and couple cluster, where you can keep adding more determinants and eventually reach the exact limit. But in practice, that's not possible because you really need to do a double extrapolation in both the single particle basis and in the determinants that you construct from the single particle basis. And when you do that, the cost becomes exponential in the number of electrons. So the most popular quantum chemistry method is what's called the couple cluster singles doubles with perturbative triples method. And that scales not exponentially, but as a fairly high power, order n7th of the number of electrons. Even with this high scaling, this is a method that works very well for systems that are not strongly correlated, but for strongly correlated systems, even this method fails. Density functional theory is cheap. It scales only as order n cubed, and it's in principle exact, but in practice, we all know that you have to make approximations to the exchange correlation functional, and there's no systematic way to improve that. Quantum Monte Carlo methods are rather versatile. They're used both for finite and periodic systems. Some versions of the quantum Monte Carlo methods have the advantage that they work directly in an infinite basis. So you don't have to extrapolate to infinite bases like you do in the other methods. They do have the downsides. Of course, they have a statistical error, and some observables are easier to compute than others. Okay, so what are Monte Carlo methods? A class of computational algorithms that rely on repeated sampling to compute results. And as you all probably know, they're used not only in the hard sciences, but even in the social sciences and on Wall Street. When are Monte Carlo methods likely to be the method of choice? When the state space is very large, so it may be discrete and very large. Let's say, by large I mean larger than roughly 10 to the 10, or the state space may be continuous, so you may have a continuous infinity, and if you're in a high dimensional space, then the methods are the method of choice. Okay, the drawback is, of course, that they have a statistical error, and for quantum Monte Carlo methods in particular, there's often a trade-off between reducing the statistical error and a systematic error. So in particular for fermions, as Martin Zwerlein pointed out, fermions are antisocial, and they result in a fermion sign problem, and that is the main thing that limits the accuracy of quantum Monte Carlo methods. Okay, in the hard sciences, they have been used for a variety of different systems. They've been used for studying models of strongly correlated systems, such as the Hubbard model. They've been used to study liquid and solid helium. One very well-known application of quantum Monte Carlo is that it's used to construct the LDA approximation, the local density approximation that is used in density functional theory. That the exchange correlation functional in that approximation comes from Sepperly's quantum Monte Carlo calculations. They're used in nuclear theory. Lattice gauge theory is a form of quantum Monte Carlo methods. The area that I mostly work in is in the electronic structure of atoms, molecules, solids, quantum dots, quantum wires. Finally, quantum Monte Carlo methods, there are both zero temperature and finite temperature quantum Monte Carlo methods, so they're rather versatile. I will be talking about only the zero temperature quantum Monte Carlo methods here. Okay, so first let's talk about Monte Carlo before we start talking about quantum Monte Carlo. Monte Carlo methods are based on the central limit theorem. So if I have a sequence of independent random variables that are drawn from a probability density function that has a finite value and a finite variance, then the central limit theorem states that as I increase the sample size, these averages of these n fluctuating variables are going to give you a Gaussian distribution. And the width of the Gaussian is going to go down as the square root of the number of variables that are average. So this is a rather remarkable theorem because the original distribution from which I sample may not look anything like a Gaussian. It may have some bizarre shape. So long as it has a finite variance, the averages will turn out to be a Gaussian, and their width will go down as the square root of n. Okay, so because of that, Monte Carlo methods become a very efficient method for calculating integrals in a high-dimensional space. So let's just compare to regular Monte Carlo deterministic integration methods. So for example, a Simpson rule. So we know that a Simpson's rule, the error converges as 1 over the number of integration points to the 4th power, provided that the function is sufficiently smooth. Okay, but now think about what happens in d dimensions. The convergence goes as n to the minus 4 over d. So if d is large, let's say d is 100 or 1,000, then the convergence is miserably slow. Monte Carlo methods, on the other hand, the error goes down as 1 over the square root of the number of Monte Carlo points, thanks to the central limit theorem. Okay, so the convergence is independent of the dimensionality of space. In particular, when d is greater than 8, then it becomes advantageous to use Monte Carlo methods rather than Simpson's rule for doing the integration. Okay, so when you're doing electronic structure methods, you're interested in how the methods scale as a function of the number of electrons. Okay, so the dimensionality of this space is the dimensionality of your many-body wave function, which is 3 times the number of electrons if you're in 3-dimensional space. Okay, so if you use Simpson's rule, the number of integration points would increase exponentially with n. On the other hand, if you use Monte Carlo methods, the number of integration points increases only linearly with the number of electrons. Okay? Of course, this does not mean that the total cost of your calculation scales only linearly with the number of electrons, because the amount of work you have to do per Monte Carlo step goes up, but that goes up only as order n cubed. And so you end up with a rather favorable scaling compared to deterministic integration methods. Okay, so now let's switch to quantum Monte Carlo methods. And I will be talking about two of them, the variational Monte Carlo and projector quantum Monte Carlo methods. So a variational Monte Carlo, all you're using Monte Carlo for is to do the many dimensional integrals needed for computing quantum mechanical expectation values. The other component of variational Monte Carlo is that your trial wave function may contain many variational parameters which need to be optimized. So part of developing variational quantum Monte Carlo is developing robust methods for optimizing many-body wave functions. Okay, what is projector quantum Monte Carlo? Projector quantum Monte Carlo is nothing more than a stochastic implementation of the power method for finding the dominant eigenvector of a matrix or an integral kernel. So let me remind you what is the power method. If I have a matrix and I want to find the eigenvector corresponding to the largest in magnitude eigenvalue, then I can repeatedly multiply that arbitrary vector by the matrix. Each time I do the multiplication, the eigenvector corresponding to the largest in magnitude eigenvalue gets multiplied by the largest number. So if I do that many times, I'm left with the eigenvector that I want. Okay, so that's the deterministic power method. And it's one of a class of iterative methods for finding eigenvalues of matrices. Okay, so other methods that may be well known to people are the Davidson method and the Lanczos method. Okay, now if your state space is small enough that you can use one of these methods, then you should. You should not use Monte Carlo methods. Okay, so typically if your state space is less than 10 to the 10, then you should use the deterministic methods. But what if your state space is 10 to the 100? Okay? That's when you use quantum Monte Carlo methods. And the reason why the quantum Monte Carlo methods work is that you never store even a vector. Okay? All you store is samples of the vectors. And when you do quantum mechanics, what you're interested in calculating is not the wave function, but the expectation values, various expectation values for the wave functions. So I can sample from my wave function and calculate the contributions of my samples to the expectation values without ever storing the entire wave function. So that's the gist of the projector quantum Monte Carlo methods. And they work not only in a discrete space and large space, but they also work in a continuously infinite space. Okay. So let's, to make that a little bit more concrete, let's introduce some notation. So let's say I have a basis, and for now I will keep the basis general. And I expand my exact wave function in that basis, and I will call those expansion coefficients E. And I can expand a trial wave function, so this is an approximation to my exact wave function in the same basis, and I will call those T. Okay. So here's the gist of variational Monte Carlo. I want to calculate the expectation value of, for example, the Hamiltonian, but it could be some other operator, for the trial wave function. Okay, so I introduce my, my states in, whoops, excuse me. I introduce my complete set of states over here and over here. And then I use my definition of the Hamiltonian matrix and the components of the wave function in that basis. So I have this. And then I rewrite this as a quantity that looks like a probability, a probability function. So this is something that is positive and it sums or integrates to 1. Okay, so this is a probability density that I can sample. And then if I sample that, then all I have to do is I have to average what's left, which I call the local energy. Okay, so in the end, I'm left with a simple sum over my Monte Carlo points of these local energies. Okay? As my wave function gets better and better, this quantity that's called the local energy becomes the energy, because then if I have an eigenvector, then when I perform the sum, I get the energy times Ti in the numerator, and I'm left with just the energy. Okay, so as I improve the trial wave function, a single Monte Carlo point becomes enough to get the energy. Of course, you never reach that limit in practice, but it tells you that improving the wave functions gives you an enormous payback. Okay, Projector Monte Carlo. In Projector Monte Carlo, you take advantage of the fact, so you are interested, of course, in not calculating the expectation value for the trial wave function, but for the true wave function, which I've denoted by psi 0. Okay, but this pure expectation value is equal to this mixed expectation value. Okay, so this equality is also used in other methods, for example, the coupled cluster method, right? Okay, so supposing I had the exact wave function available to me, or I have a way to sample it, then I go through essentially the same steps over here, and I end up again with averaging the local energy. So this looks exactly like what I did in variational Monte Carlo. The only difference is that these Monte Carlo points are now sampled from the product of the trial wave function and the exact wave function. Okay, so far I've not told you how you sample from the exact wave function. I will get to that later. Okay, so let's make things more concrete. So far I was working in a general basis. Let's say I use a basis of position eigenstates. Then, so now I have a continuously infinite basis. My sums become integrals. Okay, here's again my expectation value. Again, I choose to sample from something that is positive definite and something that integrates to 1, and I average what's left, which is my local energy. Okay, so this is what it looks like in real space basis. Okay, so what do I need to do a good job of variational Monte Carlo? I need a method for sampling the square of an arbitrary wave function. I need a functional form of the trial wave function that is capable of being accurate. And then I need a method for optimizing the parameters in the wave function. Okay, so what's used for sampling is the well-known Metropolis-Hastings method, which was originally introduced for sampling the Boltzmann distribution. But in fact, it's a method for sampling any known probability distribution. The downside of the method is that the samples are not independent. They're sequentially correlated. But one has a freedom of choice in the proposal probabilities that enter into the Metropolis algorithm. And if one makes an intelligent choice for these proposal probabilities, then in fact this autocorrelation time can be made extremely small. And so the fact that the samples are sequentially correlated is not a big issue. Okay, for the form of the trial wave function. The nice thing about quantum Monte Carlo is that one can use wave functions that build in whatever insight you have for the physics or the chemistry of the problem. So there are a variety of wave functions that have been used. For example, if you're, for example, interested in the fractional quantum Hall effect, you can use wave functions that make use of composite fermions, for example. Okay? In electronic structure theory for molecules, the form of the wave function that's most typically used is a linear combination of determinants times a Jastrow factor. Okay, so I've denoted by green the variational parameters that enter into such a wave function. So one set of variational parameters are these linear coefficients that multiply the determinants. Now these determinants are determinants of orbitals, so the orbitals themselves are expanded in basis functions. So these LCA coefficients are variational parameters. If you like, the exponents of the basis functions can be variational parameters. And finally, you have a Jastrow factor. So the Jastrow factor is what puts in correlation between the electrons in a very direct way. It keeps the electrons away from each other. And so the Jastrow factor is typically written as a product of three kinds of terms: an electron-ion correlation part, which in fact could be subsumed into the orbitals, an electron part that keeps the electrons apart, and an electron-electron ion correlation part that puts in the effect that how strongly the electrons want to stay away from each other depends on where they are in the molecule or the solid. Okay, so in each of these, one has some variational parameters, typically on the order of 25 of them. Okay, so if one looks at the different kinds of variational parameters, the number of Jastrow parameters only scales with the different number of atom types that one has in the molecule or the solids. The number of exponents also scales with the number of atom types. The number of these coefficients scales as the number of orbitals times the number of basis functions. So that scales as the square of the number of atoms. And finally, these coefficients scale exponentially in the number of atoms that you have. Okay, so the quantum chemistry methods, they just use this linear combination of determinants, and they have to use a very large number, millions or billions of determinants, to get an accurate wave function. One part of the power of quantum Monte Carlo methods comes from the fact that you have the freedom of using the Jastrow factor, and when you use the Jastrow factor, one can use a very small determinantal expansion and still get very accurate energies. So that is where part of the power of quantum Monte Carlo methods comes from. The other part comes from the projection in the projector Monte Carlo methods. Okay, so a word about optimizing the wave functions. The first thing that you need to decide is what do you mean by optimal wave function? What is the objective function that you want to optimize? And the other thing is how do you do the optimization? Okay, so there are various measures of goodness of variational wave functions. So the first and most obvious one is you may want to minimize the variational energy. Another possibility is you may want to minimize the variance of the local energies, right? Because when you have the exact wave function, the variance goes to 0. Another thing you could think about optimizing is the overlap of the trial wave function and the exact wave function. Or if you don't have the exact wave function, an approximation to the exact wave function, which I will call the fixed node wave function, which I will talk about a little bit more later. Okay? Yet another thing that you can optimize is the projector Monte Carlo energy. So, when you do projector Monte Carlo exactly, of course, you get the exact energy. But in practice, because you have the fermion sign problem, you end up calculating an approximate projector Monte Carlo energy, so you may want to optimize that. Okay? In fact, it is possible to do all of these different optimizations, but the most efficient and practical methods these days optimize either just the variational energy or a linear combination of the variational energy and the variance. Okay. So this is sort of the progress that has happened in optimization of many-body wave functions. Until about 1988, people were doing what I would call naive energy optimization. Then in this time period, most people were doing variance optimization. And then since 2001, we've sort of come full circle, and we're again doing energy optimization. And what I want to explain to you next is why this naive energy optimization does not work well, and so why people switched to doing variance optimization and then they came back to doing energy optimization. So supposing I have a set of Monte Carlo samples, and I have an approximate trial wave function. Because my wave function is approximate, my local energies will have a spread. They will not each be equal to the exact energy. Okay. Now, supposing I have a variational wave function, and now I try to minimize the energy. Think about what happens. Most of these local energies will tend to go down. Maybe some of them will tend to go up. Okay. But if I have a variational wave function with a lot of variational freedom, on average, they will go down. And in fact, they may go down so much that on this sample, my average energy may go below. So the average, the average on this sample is what I'm showing with this dashed line. It may go below this exact energy. Okay? However, when I now draw an independent Monte Carlo sample, what I will find is that the energy has actually gone up rather than gone down. So it's only on this sample, because I had a lot of variational freedom and not a huge number of Monte Carlo points, that the energy went down and went down below the exact sample. So once you realize what the problem is, it's obvious how to solve it. You solve it by minimizing the variance, in which case all these energies tend to come together, and the average goes down only a little bit. It doesn't go down as much as it did here, but this is a genuine gain, whereas this was a spurious gain. Okay, so that's why people switched to doing variance optimization. People have now figured out how to do energy optimization efficiently, and so that's why they came back to. Okay, I really need to speed up. Okay, Projector Monte Carlo. In Projector Monte Carlo, I said that we use the exact wave function for either the bra or the ket of the expectation value. How do you get that exact wave function? You get it by repeatedly applying a projector to an arbitrary state, right? So this is the stochastic implementation of the power method that I talked about before. Okay, but in quantum mechanics, you're not interested in the dominant eigenvector of the Hamiltonian. You're interested in the ground state. So what you need to do is you need to make the ground state of the Hamiltonian be the dominant eigenvector of the projector. So two different functions of the Hamiltonian that do that are either this exponential projector or the linear projector. So in both of them, the ground state, so if the E trial is chosen to equal the ground state, then the ground state will have eigenvalue 1, and the excited states will have eigenvalues smaller than 1. Now for the linear projector, for that to be true, you need to have that this tau, which is called the time step, is smaller than some maximum value. Otherwise, you get eigenvalues that are more negative than -1, and so those become the dominant eigenvalues. Okay, so the various Projector Monte Carlo methods can be they can be categorized by the form of the projector, whether you use an exponential or a linear form of the projector, and the space in which the walk is done, whether it's done in real space or whether it's done in orbital space. And finally, whether one uses first quantization or second quantization. So what I mean by that is that you have, of course, for electrons, an antisymmetric state, and whether you consider all permutations of the electrons to be the same state or whether you consider those to be distinct states. Okay, so the way you apply the linear projector is very straightforward. You know the matrix elements. So starting from a state, you sample the off-diagonal states, and then you sample them with some probability density, and then you have to reweight them by the magnitude of the projector divided by the probability density. Okay? Now, because you're doing this reweighting, you have weights of walkers, so you no longer have a single walk. You have to have walkers that branch. If you don't do that, the weight of a walker will get either extremely large or extremely small, and that causes inefficiencies. Okay. Let me skip this part. What I'm deriving here is the form of the projector when you're in real space. Okay? But since I'm short on time, I'm going to skip that and talk about the sign problem. Okay, so this is what I was talking about before. In variational Monte Carlo, since there are no weights involved, or if you like, the walkers always have unit weight, you can do a single Monte Carlo walk. When you do Projector Monte Carlo, you have a population of walkers, and they either die or they branch. Okay? And so each of these walkers can either create progeny or they can die. And you calculate an average over this population of walkers. And that is done in order to have a reasonable efficiency, so that you don't get extremely large weight or small weight walkers. Okay, so I'd like to talk to you now about the sign problem, which is the main problem that limits the accuracy of quantum Monte Carlo methods. Okay, so when you work out the projector in real space, this is what your projector looks like. You have a Gaussian term, and you have a reweighting term. Now, when you look at this, this is a positive quantity. There are no negative signs. So you may think that there is no sign problem. However, if you use this projector, what you project out is the bosonic ground state, which is not the state that you're interested in. Okay, so typically what is done in quantum Monte Carlo methods is you use what's called the fixed node approximation, where you force the projected state to have the same nodes as the nodes of your trial wave function. That's an approximation. It's a constraint. And because you're doing a constrained optimization, you get an upper bound to the energy rather than the true energy. OK, so let's think about what would happen if you tried to get the true energy. OK, so what I'm showing you over here is a schematic. What I'm denoting in green is a bosonic wave function. Okay? The red is my fermionic wave function, which is the wave function that I'm interested in. But what I have available to me is an approximation to the fermionic wave function, which is this blue curve. Okay, so now if I evolve, so what I can do is I can start with plus walkers sampled from the plus lobe of my trial wave function, and minus weight walkers sampled from the negative lobe of my trial wave function. And then I can evolve those. So if I did a deterministic evolution, what would happen is that each of my positive distributions and my negative distributions would tend towards my bosonic ground state distribution. And when I add the two together, I would get a fermionic distribution that approaches the true fermionic distribution. Okay, so if I evolve this further, this is what happens. If I evolve it further, this is what happens. And this difference converges to the fermionic wave function, which is what I'm interested in. The problem that occurs is the following. When you're doing Monte Carlo, you're not doing a deterministic projection. What you have is a set of Monte Carlo samples, and each of these is a delta function, so I cannot cancel them. I cannot take the sum and get this nice smooth curve. Okay? Moreover, what will happen is because of fluctuations, you will eventually either end up with just the positive or the negative walkers. And so you will end up with just the bosonic ground state. Okay, so once you realize this, you may think that you can solve the problem by always working in a state space which is antisymmetrized, okay, which is what is done in some of the quantum Monte Carlo methods. However, that does not solve the sign problem. And the reason for that is the following. Different paths going from a state I to a final state J can contribute with opposite sign. Okay? And so most of the time, that is the case, and you have a sign problem. Okay? There are special situations, as Martin mentioned, where the sign problem disappears. When does the sign problem disappear? It disappears when your projector is such that each column of the projector has the same sign structure aside from an overall sign. Okay? So for example, this column has the same sign structure as this column if I flip all the signs of this column. Okay? So very often people say that there is no sign problem if the projector is entirely positive. That is a sufficient condition, but it's not a necessary condition. The necessary and sufficient condition is that the sign structure is the same. And if the sign structure is the same, I can redefine my basis states simply by switching the sign of this state such that my projector becomes entirely positive. Okay. Am I out of time, or?
You have a couple minutes.
Okay.
And then discussion.
Okay. So there is if you're in a finite space, you can solve the sign problem simply by having a large number of, sufficiently large number of walkers and canceling them. So going back here, note that the sign problem occurs because you're doing Monte Carlo, right? If you're doing a deterministic projection, the fact that you have positive and negative contributions does not matter because you can just add them together and you get a net signal. You don't get a growing noise to signal problem, okay? So you can solve the sign problem simply by having a very large population so that your stochastic, in the limit of an infinite population, your stochastic projection looks just like a deterministic projection. Okay, so what was done in what's called the full configuration interaction quantum Monte Carlo method is that you have a population large enough that you can use these cancellations to control the sign problem. This only works for very small systems. But if you introduce an approximation, which at first seems like a very crude approximation, that you only allow those walkers that are on determinants that have a sufficiently large population to spawn walkers, if you introduce that approximation, then you can use it for somewhat larger problems. Okay? And so that was done by the Alavi group. An add-on to that is that since quantum Monte Carlo methods are nothing more than a stochastic implementation of the power method, what you can do is very often you have a certain number of states. So that number may be large, it may be 1 million, but it may be a small fraction of your entire state space, which may be 10 to the 100. If you have a situation where a relatively small number makes most of the contribution, then you can do that part of the projection exactly. And by doing that, so that's what we call the semi-stochastic quantum Monte Carlo method. And by doing that, you get a very large gain in efficiency. And since I'm out of time, let me stop here and take questions.